Today, we are on a mission. We're going to crack the code of a fundamental language of the universe, algebra. We'll be decoding something called linear relations, and I promise you, it's way more like a puzzle than a dry math problem. So let's get started.
First, I want you to just think about this question for a second. What if every single math equation we see is actually a secret code? You know, a set of instructions that, once you figure them out, can predict outcomes, find missing information, and even solve real-world mysteries. That's the mindset we're taking with us today. So, the code we're cracking is called a linear relation. Now, that might sound complicated, but it's really not. It's just a simple, predictable relationship. When one thing changes, another thing changes right along with it, in a consistent, straight-line pattern. Think of it like a recipe. You follow the instructions, and you'll always get the same result. All right, our first challenge is to learn how to read the code. We're going to take a set of instructions, an equation, and use it to map out a relationship. We're basically creating a table of predictable outcomes. And here it is, our first code. It says that to find the value of y, you take the value of x, multiply it by -4, and then you add 1. Pretty simple, right? Let's see it in action. Okay, so our mission is to complete this map. We've got our x inputs 1, 2, 3, and 4. Our job is to use our code y equals 1 minus 4x to figure out the corresponding y value for each and every one of them. Let's just see how simple this process really is. We take our first value, x equals 1, and we just plug it right into our code. So, y equals 1 minus 4 times 1. Well, that simplifies to 1 minus 4, which gives us -3. The first point on our map is 1, -3. Easy. And look at that. This perfectly illustrates the pattern. When we repeat that same process for x equals 2, 3, and 4, we get this completed table. See that? For every single step x takes, y drops by 4. That is the predictable linear relationship. We've successfully mapped the code. Let's do this again with a slightly different code, y equals x minus 4. Now, the process is exactly the same, but this time we'll use some different inputs. We'll even throw in some negative numbers just to see how it holds up. And here is the completed map for that second code. We plug in -4 for x, we get -8 for y. We plug in 0 for x, we get -4 for y. See? The system works every single time. It's a totally reliable set of instructions. All right, for our second challenge, we're putting on our detective hats. We're going to use the code not just to map out points, but to find specific missing pieces of information. It's a mystery. Here's our first case. We have an ordered pair, but part of it is missing. We know the x value is 5, but what in the world is the y value? Luckily, we have the code to help us solve it. Y equals -2x plus 8. So, how do we solve this? Well, we use the clue we have. We plug the x value of 5 right into our equation. That gives us y equals -2 times 5 plus 8. After a little bit of math, we get -10 plus 8. And we find our missing piece of the puzzle. Y is -2. Case closed. Okay, detective, let's level up. This time, we have 4 suspects, 4 ordered pairs. The code is y equals -3x plus 8. Now, 3 of these pairs follow the code perfectly, but one is an imposter. It doesn't belong. Our job is to find it. This table lays out our whole investigation. We're going to test each point by plugging its x value into the code and see if the result matches the y value they gave us. For suspects A, B, and C, it's a perfect match. But when we get to D, we plug in 9 for x, and the code tells us y should be -19. The suspect pair claims it's -20. Aha! We found our imposter. So far, we've always known x, and then we found y. For our third challenge, we are completely flipping the script. What if we know the final result, and we need to find the starting point? It's time to learn how to solve the code in reverse. So here's the scenario. We have our code. Y equals 5x plus 9. But this time, we already know the answer. We know y is 34. The mystery we have to solve is, what value of x makes this whole thing true? To solve this, we just have to work backwards. First, we set up the equation. 34 equals 5x plus 9. Now, to get x all by itself, we need to undo the operations. We'll start by subtracting 9 from both sides, which leaves us with 25 equals 5x. Then we undo the multiplication by dividing both sides by 5. And there it is, x equals 5. We've successfully reverse engineered the code.
Okay, for our final challenge, we are taking all the skills that we've learned, mapping, finding clues, solving in reverse, and we're applying them to a mission straight from the real world. Let's see how these codes actually work in our lives.
I want you to meet Harry. He's on a savings mission. His starting point is $110 that he already has in his savings account. Now, in the language of our codes, this is what we call the initial value. And this is his plan. Every single month, Harry is going to add $15 to his savings. This is our rate of change, that predictable amount that gets added over and over and over again. So putting those two pieces together gives us the code for Harry's savings. The total cost, C, is his starting $110 plus $15 for every month, M, that he saves. This simple little equation can now predict his savings at any point in the future. And here is the mission objective. Harry wants to buy a bike that costs $185. So the question is, can we use our code to figure out exactly how many months it's going to take him? This should feel pretty familiar. It's time to solve in reverse. We are solving in reverse. We know the final amount, C, is 185. So we set up the equation. 185 equals 110 plus 15m. We subtract the 110 he started with, leaving 75. Then we divide that 75 by the 15 he saves each month. The answer is 5. It's going to take Harry exactly 5 months to save for his bike. Mission accomplished. So, you see, these aren't just numbers on a page. Linear relations are codes that model the world all around us. They help us plan budgets, they predict travel time, and so much more. You've learned how to read them, how to use them, and even how to reverse them. So the only question left is, what code will you crack next?